No, go. Good afternoon, everyone. Welcome to the Iceland Ocean Cluster, and also we have people online too. We've got, I say, the highly technical younger people in my team are live streaming this on YouTube. So there's people online, there's you guys in-house. So welcome. My name's Alexandra. I'm the CEO of the Iceland Ocean Cluster. So we are, the house that you're in is the Ocean Cluster House. We're an innovation hub and network connector that's all about creating sustainable value in the blue economy. And in this house that you find yourself in today, we have more than 70 companies that are working in and around the blue economy, from brand new startups with a cool idea that are just getting started on their journey, all the way through to big international companies like JBT Marel. And the thing that we focus on is bringing people together like yourselves so that great ideas can happen in the blue economy. We're especially happy to be involved in this Blue North project. It's really exciting to think about Copernicus data and ocean data and really how important it is to have the information about our ocean ecosystems to make good decisions, to build great innovations that are good for that triple bottom line for people, planet, and profit. So we're thrilled to be involved and to work with the great teams at Náttúrufræðistofnun and Háskóli Íslands. And actually, you're going to hear from a couple of our exciting blue economy companies in-house today that are using ocean data to do amazing things. But I won't steal their thunder by telling you about them. And I'm actually just going to pass directly to Ben, who's going to introduce himself from my team in the Iceland Ocean Cluster. So thank you all for making the time to come. So, clap you guys.
Hello everyone, greetings. It's a pleasure to be joining you today. I'm hosting this event. I just want to say a few words. My name is Benedek Reguzzi, and I'm working here as an innovation project manager. And actually the first time that I experienced using ocean data was at the class of Angel, one of our presenters today. So this is where I really learned about the importance of using this data that we are collecting. And also during last year, when we actually hosted the Copernicus hackathon, that was really focusing on bringing all of these actors together, and really what basically also in alignment with the establishment of the Iceland Ocean Cluster, because we, as Alexandra mentioned, we really want to bring together all of these multidisciplinary actors so that they can solve some of the biggest challenges that are being faced by our oceans. And I think this hackathon as well, it was such a multidisciplinary collaboration, and even the ideas really showcased how creative and innovative ideas can actually emerge by bringing all of these different actors together. So for example, one example was capture that came out of this hackathon, and basically they came up with the idea of using that Copernicus ocean data to basically find the most suitable locations for seaweed farming, for macroalgae farming. So just a few examples of this, and I think this really showcased the importance of this ocean data. But with that said, I really want to welcome you and pass it to the next speaker, Marco, who will tell you a bit more about My Ocean Viewer.
Thank you for being here, everyone. My name is Marco Pizzolato, and I'm working at Náttúrufræðistofnun. I'm a GIS specialist, and I'm also the representative to Copernicus for Iceland. So I would like to introduce you today to the project. First of all, we have this, it's called Copernicus National Collaboration Program, where every state participating in Copernicus has a say and has some activities that can be planned, and we get funding for actually enacting them. And the project here in Iceland is called Blue North. And in this case, we're here at the Copernicus Marine User Forum in Iceland. And there will be other events like a workshop and a hackathon. A hackathon will take part somewhere in the autumn this year, and the workshop in late spring, probably. And it's all about learning about the data, how to use it, and then with the hackathon, the idea is that we can actually, how can we start using it and bring it into idea that then have a grip, actually. And this is the picture from the hackathon last year that Benedek was talking about. So for more information, we have also set up a website which introduces general Copernicus, and it's called copernicus.bis.is, where there is a section only about marine, and there is some examples on how to use marine data. There is, for example, also tools how to learn and start downloading the data. So it illustrates a little bit the process to go through. So this is the Blue North project, which organizes this event. And I want to introduce to you quickly what Copernicus is. Maybe someone has heard of it, someone not, it's okay. So Copernicus is the Earth observation program from the European Union. And it's split into 6 main categories. So we have the land part, which collects data about land cover, land usage, how the land moves with earthquakes, and so on. Then we have the marine part, which we will be focusing on today. And there, I will present all the details on that later. We have the atmosphere part, where we have also a national collaboration program, which monitors, for example, dust and air quality, UV light, and so on. And this data is then collected to help policymakers good decisions. We have then the climate change part, which focuses on climate change itself and monitors trends and evolution into future. We have the emergency management service, which is about managing catastrophes, for example, earthquakes, floodings, and so on. And then there is the security part, which is mostly a closed service for the member states and, for example, also Iceland, to access data from different satellites, which are more for security purposes. So, for example, in Iceland would be the Coast Guard, which has access to such data for making decisions. Yeah, so as I said, this is like Copernicus has different sectors, and now we're focusing on the marine one today. And I would like to let Copernicus Marine Service kind of introduce quickly themselves, and then I will go further into that after that.
Our ocean is vital for human well-being. The future of humanity strongly depends on the ocean's health and on our ability to monitor it. Did you know that the Copernicus Marine Service's mission is to monitor the ocean? We provide 4D regular, authoritative, quality-assured information about the ocean, available for free and accessible from anywhere in the world. We distribute data from on-site buoys and satellites and from the latest science models in order to know more about the past, current and future state of the blue, white and green ocean. We make ocean data available that can be used to create applications for a wide range of actors in both the public and private sectors. We also support EU policies and international legal commitments related to ocean governance, catering to the needs of society at large. But you know what? We're not just a data provider. We also offer a large range of services for our users. Because our mission is to empower all users, from scientists to policy managers to private companies, who want to drive the blue economy and scientific innovation. We are there to support you anytime, anywhere, thanks to a dedicated help desk team, a chatbot, FAQs, a collaborative forum, and tutorial videos at your service. We organise events, webinars, and online training sessions to share scientific knowledge and promote sustainable ocean initiatives. And we continuously collect feedback from our users. We know one thing for sure: we need you. We need you to make the right decisions for the future. For a blue-green deal, a healthy ocean, a healthy planet, healthy people.
So yeah, this was a quick introduction. A lot of information in there in this video, but summarizes a little bit what Copernicus Marine is doing. I want to stress there that it's meant to provide free and open marine data and services to open to everyone, so you can actually see it, download it, access it, and work with it. And the services connected to it is already pre-processed so that you can actually make decisions out of it. And they support with also expertise to the users. So for example, they have a chatbot and so on that you can directly ask, and also send them a line, an email, and they will help you to understand the data and improve for your work. And then their goal is also to help the blue industry, and we are here in the Ocean Cluster because it's maybe the beginning of startups and companies in the blue industry. And so the idea is that the data empowers new technologies and innovation in the sector. And then there is among us also scientists, and that's important to have this data for scientific innovation available. But why does it exist in the first place? Like, why did someone decide to make Copernicus Marine? Like, why is this marine observation platform? And the goal is to provide a sustained and operational ocean monitoring system that can continuously monitor, because maybe before it was scattered between every country doing something and they had needs, but at scale you can easier start to merge the data together and build a bigger platform and network of sensors and everything. And integrate observation and models into a coherent view, so that you can use a model here and a model in another part of the world, and they kind of are well integrated together. Make high quality ocean data openly and reliably available, and support evidence-based decision making, so that policies and decisions are not based only on feelings, but they're based on science and data. And for that, it needs to be available, and also available in an easy way to access, so that it's at your fingertips, basically. So I want to introduce maybe some use cases in a broad way. So I will not go into detail. We have Icelandic use cases later on in this session, but I would like to introduce some use cases to give you a general idea what this could be used for. So the marine data can be used, for example, for rescue missions in the sea, at the ocean, to monitor the drift of objects. So if there is some vessel which is not able to navigate, and it will be drifting, thanks to currents and so on, you can actually predict where it would be drifting to. There is also the use case, for example, for optimizing route finding, so where to save fuel for shipping and for the shipping industry, for fishing and so on. There is the use case for safety. We're in a country kind of high up north, and we have the problematic of sea ice, especially around the Greenland part, and we will hear some more later on, but to navigate safely. And for example, also oil spills or other spills in the ocean for environmental purposes, so to monitor that and kind of make the correct decision on how to take action towards that. Then there is the coastal part and coastal management side to protect communities. For example, this is an image of, I think, Athens. And so you want to protect local communities from, for example, sea level rise and make predictive action and planning on site, and how to kind of develop the community in a sustainable way so that you can stay close to the ocean. There is the climate monitoring and research part. All this data produced can be used, for example, to monitor changes in temperature and, for example, heat waves and so on in the ocean, and that affects basically sea level rise and other parts, and, for example, also the currents in the ocean, how the currents, for example, the how it's called, the amok, which brings hot water from the south, from the Atlantic, how that is affecting us, and how to monitoring it, in a sense, the evolution of it. We have the environmental protection part, which can be to monitor habitats for plants, algae blooms, and so on. Track plastic, which is actually one of the newer use cases, that how if there is some river which emits plastics into the ocean, to track where the plastic will end up, or where is the likelihood to find it, and the biodiversity and the health of the marine species. And last but not least, the blue economy and fisheries, to kind of also improve our economy and our food system and safety, how to improve fisheries, to know where to find fish. We will hear about that later on. And then for aquaculture, to monitor parameters for the water in the ocean, and for example, renewable energies, wind and wave, and so on. And we're here today because it's really important for us as Iceland, which is a nation which is basically surrounded by the ocean, to have a say in this. We are maybe not so many people, but we are kind of, the ocean is a big part for us. And it's important that we have a say to Copernicus and Copernicus Marine, and bring our voice to them. And so today the idea, and also how the event is structured, is that we together, there will be an interactive part and so on, that we together can bring a feedback on what are our needs, how could I use it, or what is not available that I would like to be available, and how this could be possible, so that in future investments could be done and decision can be done to address these needs from Icelandic users. So I can then directly bring this information back to the Copernicus configuration and where the decisions are made, kind of. So it's important today that you voice your needs and you also talk together, because maybe someone in this room is already doing something similar, and we want to use the knowledge of everyone and the skills, so that we can find common ground. Because maybe there is one expert here, one expert there, and I have a use case, and the expert doesn't know about my use case. So today we would like to bring everyone together and have the opportunity to talk and exchange. And in order to do that, we need also maybe to know what we're talking about. So the Copernicus Marine is kind of structured in the following way. We have some satellites that collect data. We have in situ data collection, and we have then from that we're building models. And I think we have people in here that will explain you way more in detail about the models and so on. So let's focus quickly on the satellites. So maybe you know that the Copernicus program has so-called sentinels, which are satellites with the primary purpose to monitor the environment and the planet Earth continuously. So we have Sentinel 1, 2, 3, 4, 5, and 6 that are in orbit, and their number doesn't mean that they're in a there is only one. There is multiple of each one to monitor a specific thing. So, for example, Sentinel-1 is a radar one, which collects different data than Sentinel-2, which is multispectral, which collects more light. So it's different signals that are collected. And with this, for example, with the spectroradiometer, we can collect information about chlorophyll, or the infrared radiometer can collect information about temperature. And for example, altimeters can collect the level of the sea, the elevation and the change over time. And so we have these sensors which are collecting data from space continuously. So we have a huge quantity of data, but we need a way to kind of verify it. So there is the in situ part, which collects on-site with sensors data that we can then compare. For example, that will be some floats, where, for example, from Argo, we have sea tags on animals. We have sensors on boats and buoys, which measure temperature, salinity, and so on, which then can be brought back and combined with the data from space. Here is an example. There is this site called marineinsitu.eu, and there is data from Reykjavik here, which the Marine and Freshwater Research Institute is providing, for example, which is measures temperature. And there is also Vegagarden, which is providing data about the sea level. And so we can see different types of sensors, and they're all over the place monitoring continuously and collecting data. And so then comes the part of the model, which I'm definitely not the expert, but there will be later on some more expert person talking about it. And the idea with the model is to combine those things in order to make prediction into the future, and also to understand the dynamics of how the ocean and this ecosystem work. So we combine the data from space with local sensors, and then try to model how the interaction work, and kind of be able to predict and take predictive action. This, for example, also we can do this with sea surface waves and tides and so on, kind of, but a bigger scale. So maybe the sensors collect data individually, but we want to make that into a model that is continuous. So yeah. And these models are in 4 dimensions. So when you will look at the data, you can imagine this as 4-dimensional. So you have 3 spatial dimensions and 1 temporal dimensions. The spatial dimensions vary between data sets from 0.3 kilometers to 100 kilometers. And the temporal time frame can be decades of data and into up to 10 days forecast into the future, so from these models. And I maybe want to mention, some of you might know, some don't, because you will encounter this term if you ever end up looking for data sets. You might end up in seeing forecast, which predicts the future. We have nowcast, which is the present data that we have from our operations, and hintcast, past data. And the term that I want to stress maybe here is that we hear in the data sets is reanalysis. What does that mean? That's like, it's a long-term model that has been corrected by data that has been collected kind of from sensors and satellites and so on. So this is just to clarify, if you hear during the day today reanalysis, that's kind of what it's referring to. The data is also split in global data products and regional data products. There's a difference there, which the global covers all ocean and is often in coarser resolution, and it uses, the advantage though is that it uses the same model for different areas, while the regional models are in a limited area, but they give you a higher spatial resolution, and they offer better models for the local environment. When you look for data sets, you will find this definition, and so you can know what to look for when. And maybe finally, they're split into 3 categories, these data sets, which is the blue ocean, then we have the green ocean, and the white ocean. So, and they're continuously, these data sets are continuous temporal data sets, as I said before. And I will go into depth now what blue, green, and white ocean mean more into detail. Yeah, so the blue ocean is the part which refers to the physical part of the ocean. So, for example, it can be salinity, it could be temperature, we have the waves, the winds, and the sea surface height, and all the physical parameters, and also the velocity. So, if I say velocity, it's how the water moves, but then you have the currents, but it's you have data sets about velocity in one direction, in the other direction, and also the composed velocity of it. So you can imagine what the data sets look like. And I think we will hear more in detail also today about it. This is to give you an overview. Okay, this is physical parameters, blue. Then we have here the example of the potential temperature, and this is an example of the data set that you can find in this physical part, the blue one. If we go into the green ocean focuses more on the living things and the bio and geochemistry. So we have, like, for example, chlorophyll, which is our little plants in the ocean. Many of you probably know, but I just want to make sure that everyone is on the same level. Those can be then eaten, for example, from zooplankton. So we have some data set about zooplanktons. We have data about the fish, the nekton part, kind of. We have data about the oxygen state of the ocean. So, like, also fish need oxygen to live, so we can predict how the environment is evolving and make decisions based on that. And we have, like, plenty of data sets related to that that then go into detail for each category. And then here is an example of how this data looks like for the green part of the ocean. This is chlorophyll. So you can see concentrations, lower activity here, for example, and higher concentration here in this model. Then there is the white ocean, which is focusing on the ice. So this is normally at the poles of the planet. So we have Antarctic and the Arctic, and we have, and this model is used to describe kind of the life cycle, how the ice evolves over the years, and to measure trends, which then can be used for climate modeling and so on. And so it's monitoring the ice. We have the ice velocity, we have the snow, which then affects also the albedo, how the light is reflected from the ice. We have the monitoring of icebergs for example, ships and ship traffic. We have the monitoring of sea ice thickness and sea ice concentration, like how concentrated sea ice is in a certain area. And here is an example of a data set which shows the sea ice thickness. I think in this image is not really visible, but here we can see it's way thicker than actually here, and this goes down to Greenland, and then close kind of here to Iceland, and that's how the status often is in the winter time. Yeah, and all this data in these different categories, you can actually access it yourself. So we have this website called data.marine.copernicus.eu, which allows you to directly see the data and access it, download it, and use it for whatever purpose you want. And so all the introduction I did now is to help you, if you ever need, that you can go to this website and understand in which direction I want to move to find this data. So you can, here in the filtering, you can put some text, or you can select some areas and regions, and set a time. Since there is temporal data, you can also look only for data since the last year or something like that, or future like forecast data and so on. And there is a plenty of data sets. There is more than 300, so that you get a kind of idea how much data is available. And it's split in these different categories, so you will have an easier way to find your way. For those of you which are more advanced users, I want to mention that there is also QGIS plugin, which is a GIS system openly available, that allows you to download the data directly in that software. Or for the ones that are more used to work with Python and programming, there is a Python package called Copernicus Marine, which allows you to automate download, automate data collection and requests, so that if you need to do it at a large scale or in an operational setting, you can get this data continuously and with scripts and so on. And this is how it looks like here. Yeah. Okay, now that's how you get the data and you can kind of access it. But what if I just want to see the data? So there is this visualization tools from Copernicus Marine. We have the MyOcean Learn, which is kind of introductory, gives a little bit of overview how this can look like on a globe in 3D and temporal way, but it doesn't allow you to interact with it, kind of. You can just look at it. Then there is the MyOcean Lite, which allows you to start to use the data in a way and interact with it. There is more data sets available. And then you have the MyOcean Pro, which we will have a session later today on how do you actually access the data, and you can actually make graphs and extract information directly from MyOcean Pro. And maybe I just run over them quickly, how they look like. This is the MyOcean Lite, MyOcean Learn, which has more the awe effect. Oh wow, what is this data, how it looks like, how it changes over time, and it's cool to look at, but you can do little with it to work. Then you have MyOcean Lite, which looks already different. You have here a timeline at the bottom and a depth also in 3D, so you can also define what depth of the ocean you want to analyze or look at. And you have the data sets here to the left available with a legend on top here. But then when you go into the more depth, which we will hear more later, you will have more data sets available, you have more tools to choose from, and you will have also the ability to make graphs and interconnect data and analyze them. So you know there is plenty of tools to visualize all this data for you as users. I want to also mention that they produce some policy tools, for example, and also ocean state report that every year kind of says what state is of the ocean, and allows you to have an overview. If you simply have the question, what's the state of the ocean, then they publish some policy-related more tools, kind of. Yeah, and so this is the website, how it looks like when you access Copernicus Marine. And you see here on top there is access data, which will lead you to choosing if you want to visualize it or access the data set itself. And there is also some example use cases and so on. Yeah, so just now we went all the steps on understanding and how I access and work with this data themselves. Now I want to illustrate to you what's the trends of future evolution of Copernicus Marine. So they develop the colors here, kind of show what type of the ocean is. That now should be clear. For example, the blue ocean improvements are blue. Then we have like the white ocean is this grayish one, and the green ocean is like greenish. So the improvement in data sets over time. So they plan to improve resolution. They plan to improve services and data sets available. And I will go maybe more into details in this slide on the kind of key points of their evolution of the services. They want to increase the forecast length So one of their goals is to be able to provide a forecast that is more than 10 days into the future. They want to improve the spatial resolution for some data sets in order to be maybe more accurate for certain users. And we are talking about this, not that all data sets will increase in the resolution, but some of specific one, which that's exactly the case where we have to send a request, hey, we would need more of this data, higher resolution, because then the money can be invested into improving this data if we have a use case for it. So that's why it's an important part of why we're here. Is to, like, if someone has will ever encounter that there is some need, I need higher resolution, I need higher temporal or something, we can send this request and let know that we have this specific use case that should be thought about. And I want to mention here also they're working on this digital twin ocean called EDITO, and the marine data sets Necton. So maybe EDITO, the digital twin ocean, is a platform where this data is all included and people can start to use this to produce tools. So you can directly access and produce tools yourself. And so basically you can connect the data and make already a product that then someone can use. In a sense, this is great for startups if they want to produce with ocean data. This is a platform where all the data is kind of available and you can interconnect it to produce apps, for example. And there is, like, I want to mention this Horizon project, the Necton project, which will improve the biogeochemistry part, which is the green part of the ocean, with adding new data sets for example, marine pollution, the benthic habitats, and the higher trophic level, for example, bigger fish species, and so on. And this is all the data sets that will be available will come in the coming years, and it's being researched on in this Horizon grant, and will be added to Copernicus Marine. So we have, for example, pelagic biogeochemistry. We have the benthic part, for example, oxygen, CO2 absorption from the seabed, and so on. We have Necton part, which is more about fish and the fish populations, and we will have the stressors, which is not available now. So it's like more about, for example, mercury in the water, oil, and so on, and they're being developed in models on how to monitor this. So this I wanted to mention, so if there is question, this is coming and this is where they're working on. I want to conclude here with this introduction. If you have further questions, you can simply send me a line. You can scan the QR code, or you can find my email on copernicus.gis.is for further information. And I would like to thank you to be here today and to participate actively in this user forum. I need to mention that this is sponsored from the program Copernicus and program of the European Union and Copernicus Marine, which is implemented by Náttúrufræðistofnun Ocean. And in this project, as I said before, is Háskóli Iceland, the Iceland Ocean Cluster, and Náttúrufræðistofnun. Thank you very much for this. Now, next person coming is Ingvi, if I'm correct, from Hefring Marine, and I will give you the thing.
Okay.
Yeah.
Yeah. Hello, my name is Ingvi. I am the head of engineering at Hefring Marine. I'm going to tell you a little bit about Hefring Marine, what we do, the data we collect, and what we do with that data. So, yeah, like I said, I'm the head of engineering. If the CEO was here, he would start with a slide about what the company does and the features, but I'm starting with how we do it. So What we do is we put a computer in boats, mostly small vessels, but also larger vessels. We connect to the engines and everything on board, and we collect all the data we can. Connect engine data, tank sensors, everything. And we also install our own accelerometer, and we measure all the movement of the vessel. And all this data is uploaded in real time up into the cloud. And there we build on this data all sorts of features, which I will get into. So what data do we collect? Lots of data. Seems to be missing some rows there. But yeah, so we collect the location, the speed, the heading of the vessel. We collect from our accelerometer, we collect the precise movements of the vessel. Like every 20 milliseconds, we know exactly the acceleration, the orientation of the vessel, so we know how it moves through the ocean. We collect the engine data, the RPM, how much fuel the engine is using, your battery voltage, your alternator voltage, everything. We collect like AIS data, which is data the vessel gets from other vessels around, and weather data from weather stations on board, if there are any, and even more data. Every vessel is different what's available. Sometimes they have tank sensors or whatever, all sorts of things. We collect it all. And it is a lot of data. So right now we have billions of data points. We collect the data, which is like sailing around the Earth 40 times, hundreds of thousands of hours, 75,000 trips. This represents all the data all of our customers have collected for 3 or 4 years. And then what do we do with this data? We built a number of different applications. Our first application was safety. So the first product was something we call Safety Speed, which was aimed at these kind of tourist boats, these high-speed rib boats, which we have here in Iceland. They go out very fast, they're full of tourists, they get a lot of slamming impacts, and there have been a number of incidents where people get seriously injured, break their backs in these boats. And the first product was an AI model which calculates a safe speed to go based on the current sea conditions. And it just shows the operator directly this one number. This is your safe speed. And this was a very successful product. And then we built a number of other products on top of this. Similar concept for fuel optimization, where we built an AI model that models the fuel usage of your vessel, and based on the current sea conditions, it recommends like the speed that saves the most fuel and minimizes CO2 emissions and so on. But we're always adding more things because we have so much data, and it's a great platform for all sorts of things. Since we have all the data in real time for all your vessels, it's a great fleet management system. So you can see where all your vessels are and what they're doing. Planning things, you know the readiness of all your vessels for search and rescue or military applications. Training, we know which operator, we keep track of which operator's captain is captaining the vessel at every time. So we can create statistics for fuel usage or safety for every operator, and that can be used for training. And it also, like in some companies, it creates like a healthy competition between captains who gets the best safety score or the most fuel efficiency and so on. Maintenance, we have data about all your engines and so on, and we are building predictive maintenance features for predicting. We can see when the voltage on your alternator or batteries are dropping or changing and so on. So lots of things. And also just data analysis. We are this platform that collects all this data, and customers can get data out of this platform. We have APIs and so on. So if you have a data warehouse or data team in your organization, they can plug into our system and get all this data. I heard you guys like maps. So to show you some views from our product. So this is from our main console, web console. Here's a view of a particular trip which the vessel did, and the fleet manager can delve into this trip and see exactly the impacts that happen, the alerts that are generated, and so on. And yeah, the system can be set up to generate alerts based on whatever you want. It's a very flexible rule engine and so on. Some customers prefer to have like a nautical chart, and we offer that as well. And we recently integrated, it's a little, maybe a little bit difficult to see, but we recently integrated AIS data, so you can view the AIS data collected by your vessels in the console. And we are planning on building features on this data. We have customers who are like operate pilot vessels or towboats, stuff like that. They need to intercept a particular vessel at a particular point, and that's an optimization problem. You don't want to go too early or too late or too fast. You want to minimize fuel usage and waste of time. So we can tell you exactly what speed and what time you should go to meet this vessel at this point. Yeah, here's a view of the alerts the system has generated. So just one view of, like, this is for a 30-day period for a particular customer. They've set up all sorts of rules for like when a vessel enters or leaves a particular geofence, or some engine problems, impact events, and so on. And here they can like dive into those and zoom into particular areas where a lot of alerts are happening. Yeah, this is very dark, but what this supposed to show is like you can delve into all this data we have on the map, and some vessels have, or pretty much all vessels have, water depth sensors. And here you can see for a particular vessel, for a particular period, the water depth measurements that vessel has done. You can see shallow areas and so on where it has gone. The core features we built on is this impact analysis, using this accelerometer data to generate insights. And we have so much data that we can do a lot of interesting data science. We are working with academics who are getting access to our data, and they are currently in the process of, like, we are preparing papers which we will publish soon. It's kind of challenging the kind of accepted models that are used for wave frequencies, like the distribution of wave impacts and stuff like that, which is generally used in, for example, like modeling for shipbuilders and all sorts of applications in the marine space. And like the accepted formulas and distributions that are used today are, none of it was based on as much data as we have. It's just statistically modeled or based on very limited data. And we are finding that, yeah, it's not, the models that have been fitted are not exactly the best. We have slightly better data. So that's something we're working on as well. These are just some graphs showing different distributions on different impacts, magnitudes, and the frequencies of those and how likely they are and so on. So we have so much impact data here that we can start to cluster them and profile different types of impacts. So most impacts are wave impacts, just slamming into waves. But there's all sorts of other things. You can run into anything, and you can have freak things happen. But once we clustered them, we can start like analyzing them. We can recognize weird impacts, which are not normal wave impacts. We can flag them and to the vessel operators or fleet managers. And then we can give them a lot of insights into exactly what happened there. What angle on the hull, where did the impact happen, and so on. And characterize it in a lot of different ways, and tell them what else was happening on the vessel at the same time. Here's an example of like an impact event, a real one that a customer had, where The impact is not significant. It's 1.3 G, which is not really anything. But the system flags it because the water depth is really shallow. It's less than a meter. And the engine RPM dropped significantly at the exact same time. And this indicates there was a propeller strike. And when we look at the satellite image, we see that there is a sandbank there. And they clearly went into the sandbank and grounded the propeller. And this is something we can pick up automatically and flag and tell them exactly what happened. Yeah, so that's kind of an overview of HAPRING. We have a lot of data. Questions? Thank you. Yeah. Yeah. No, I don't know. I know we have customers who've talked about this, and many of them are interested in this. And we are in contact with another company that does something like this. They have like hydrophones placed around harbors, and they can triangulate the position of whales that enter the harbor and so on. And this is something we might look into integrating as a data source into our platform, because yeah, one of our customer bases is these kind of people who manage harbors, and this is one of the things they might be interested in, and something we could put in. So I think we don't use any direct use of Copernicus data. We use weather services that probably do. We have like a number of weather services that give us sea state and yeah, and weather data and wave height and all sorts of things. So yeah, it's really indirectly that we're using it. Yes, that's one thing we have to deal with in our analysis. We are very biased. We're not particular types of vessels which operate in particular places. Our data set is very biased towards vessels that operate all the time. For example, these kind of pilot boats which are operating pretty much 24/7 versus fishing vessels or other vessels. Yeah, so that's something we really have to work on, like when we're extracting data sets, to limit it to specific vessels, and yeah, exactly. So, fair point. No, not that I know of. We don't have many vessels in the Mediterranean. It's mostly North America, Northern Europe. Yeah, but we have some around. Yeah. Yeah, this is something we're working on to be able to get more out of our data. We have implemented like novel methods to automatically detect like the orientation of the sensor and so on, because like we're not in full control of how the sensors are installed. We don't go on board all these vessels. So we've implemented methods where we can automatically detect the orientation, but the placement matters, and that's something we're working on as well, like figuring that out so we can like virtually determine like what's happening on different, like if we assume it's a rigid body, which like most smaller vessels, you can make that assumption, then we can extrapolate like what was the impact somewhere else on the vessel where the sensor is not located. But that's something, yeah, we have to work on. Any other questions? All right. Thank you very much.
There's some free spots along the way.
Yeah, that's,
Hi everyone. So my name is Sveit, and I'm one of the founders of Greenfish, and I'm the CEO there. So Ben, you can go to the next slide. We're having a little technical issues, so Ben will be my assistant today. So I'm going to keep it brief about the history of the company. So Greenfish is founded in November 2023, and it actually comes from my bachelor essay when I'm writing the bachelor essay in my business administration at the University of Reykjavik with the headline Innovation with Artificial Intelligence. To be really honest with everyone here, my only goal with this essay was to finish it with at the least amount of time, with a minimal effort, get my degree and get on with my life. But when I'm conducting interviews with some of the top managers and CEOs in the fishing industry, it dawned on me that one part has almost been completely left behind in the recent years. We of course have huge development in vessels, processing, but when it comes to tools that help the sector decide where they should send their vessels out, the development is almost zero to none. We of course have the information system, which shows ocean heat, current, like we have in this data, but there's nothing that combines everything in this knowledge. And then you have of course the fish finding sonar that requires you to be out in the ocean and near a potential catch. So that's why we founded Greenfish. Greenfish won the North Atlantic Seafood Innovation Award, first of any Icelandic company. Today we have an office here in Reykjavik and also in Denmark, and there are 10 full-time employees in Greenfish, ranging from space engineer to physicists, AI experts, and computer science. So it's a quite diverse team, and I can guarantee you, without founding Greenfish, none of these people will ever work in the fishing industry. So it's completely new knowledge which we're bringing in. But saying all that, what does Greenfish really do? So Ben, you can go. So Greenfish developed tailored fishing prediction models that give the user 8 days forecast of the fish location, quantity, quality, and possible catch composition. And every 6 hours, the model readjusts itself. Today, Greenfish has users all around the world in every major ocean zone, and Greenfish is the global leader of making these tailored prediction models. And we work with industry leaders that are signing 2 to 3 year contracts with the company, where we take their fishing data, combining with like the Copernicus data, and we train their own specific models. It's their exclusive model and no one else has access to them. You go to the next one. So here is one model for yellowfin tuna in the Indian Ocean for one of our customers. And this is the UI and how we represent it. And it's just similar to a weather forecast. You just scale it around, and then you have a probability of why it should be there. It's 94% chance for it to be straight in this spot. And every time the ocean changes, the ocean temperature, currents, or the factor that has the most impact on each species, the model recalculates itself and it captures that. And this model is actually a biomass model, so it's not taking only factors of where the most probable factors are for the fish to be, but as much of it as possible on this point. Here's just give you an example of how vast the ocean can change just from 6 hours intervals. Here you have 86% chance on this spot finding mackerel. Only 6 hours later it goes to 56%. And the mackerel in our data is very, very sensitive to heat and current under 25 meters depth. Yeah. Here is one of our users in South Africa using our system. And as you can see, so this is the track of the vessel, and this is just recently, just go straight to just the red dot, which represents the density of it, fish, and it just can go straight back. Yeah, next one, man. Here's one of our Icelandic users. This is for herring, and this is Jón Kjartason from Eskja, the pelagic company in the east. It is AES track going straight to the predicted spot, going back. And we have hundreds of examples like this. And here's mackerel, and I don't know if you're familiar with mackerel, but this species is absolutely ridiculous in how it behaves. It cannot be still Faroe Islands, also in Chile, Ecuador, Peru, which we have users. So we didn't really start with the most easy species, but that meant all other species were quite easy to make the model for. And the model architecture is developed that we can predict any species in any ocean. So we have already archived 20 years of satellite data in all oceans back in time, and then we connect it to the forecast of these satellite variables that the model finds that has the most impact on the behavior for the recent years. Yeah, but here we're using it in reverse. We have many clients in the US, and of course, having a location model will save you time and fuel, but you can actually use it in reverse. That here we're showing zones for species that you cannot fish. You don't have quota for it, and they're actually protected. So here we're using it in reverse, and these are the zones that these companies should not try to get this fish as unwanted bycatch species. And in the US, the regulatory regarding especially salmon bycatch is really, really strict. So this is actually one of their only tools that they have before the vessels leaves the harbor. Otherwise, it's just a sonar or just calling your partner who is already out on sea. So in general, this is the best information that they have to make some informed decision and responsible decision before they do anything. Here is something that it's completely new for greenfish. So of course it's great when you find the fish, but if you lose the spot because it's 6-hour intervals, then you can actually just put down a spot there, like where the red dot is, and the system will drive 100 and up to 1,000 simulations based on every satellite variable at the time of where the most probable landing zone should be. Really important, especially for the guys like the Icelandic fleet with the blue whiting, if the fish is going to cross into our fishing zone or not. Where should it wait behind the line? So this is first ever made, and all the arrows represent one simulation. So these guys, when you're out here, it's pitch black, it's horrible weather, this is the only tool that they have to know where the fish is going to be, and this is tailored to every species. So this is, I don't know, yeah, that's bluefin tuna in the Mexican, yeah, around Mexico, I think. Yeah. This is also a new feature because positive data where we train the model is all fantastic, but we also need negative data, meaning that our users can recalibrate the model themselves. So here is one of our users in Yellowfin Shoal. He finds fish, let's say here, he will just put down a dot, and then the model know here is biomass, and then the model will recalibrate itself based on that information. So this is a very impressive feature that we hope to be automatic in the future when we start integrating the sonar with they just completely give the system new data. Yeah. And then we have this, just the AIS that they use, and Greenfish uses one of the fastest AIS available. This is come free with every user that we have on our platform. Next one. And here we have just the basic ocean variables if the user wants to have the basic features of the variables into the UI. So he can stack them up just like you with the Copernicus data and everything inside the platform. Also, here Greenfish was used for the first time with the Marine Research Institute for the Cape Land last year, and so it's also used around the world for that. So yeah, this is Greenfish. Thank you. Any questions? Yeah, so we get the fishing logs data, And yeah, we get that and combine it with the historical satellite data. Yeah, that's how we do it. Yeah, so it depends on what you want to predict. If you want to predict sizing, which we do in the bluefin tuna, we only target 70 to 90 kilo fish. It depends on the data set, but in the end, this is the best information possible for them. Yeah. Yes. Yeah. Yeah. For the size. Yeah. Yeah, sure. So they use the platform we hand it out, and the fleet manager uses it, the CEOs, and also the captains. And they're just constantly in the program, just showing where it is. But with the just responsible fishing, then of course many of the companies wants to do better in sustainable practices. And Greenpeace is actually used in for that in many sustainability reports for the company. Let's say American Seafoods. They're they're saying we use Greenpeace with the data we have to make the responsible decision that we most responsible decision we can do, and we only want to target this certain size because the other size is not ready, and also with the quality factors we can go into the pelagic with fat versus oil or protein also. So it's also you're lowering costs, but at the same time you're maximizing the value extraction you can have from the ocean. Yeah. Anyone else? Yes. Mm-hmm. We have not made a global map for everything, but our biggest model is the whole uh, South American coast for the mackerel. That's a huge model. Yeah, that's a uh, mm, yeah. Yeah, you want to show it? We want me to show it right now? I could do it. Yeah, yeah. I mean, if I'm getting a question, we already have like the system is for all of the world, but the companies will never let me have it publicly. But we have some. I mean, we have data from the government of Mexico, Chile, Peru, Iceland, Norway. And we have fishing data all around the world for our own internal analytics, but we figured out quite fast that that's not really good for the model. That's a reason why, let's say, Bream invest in their really good captains. So when you're combining all of the fishing data in one pool, instead of just the premium captains, you just want the model to learn on the knowledge with the premium captains, and that's why we moved into the tailored model, where the companies make their own model on their experience, and they own it, confidential, and giving them, of course, a huge competitive advantage to the companies who don't start developing their model, because you know how the development is in this. It only gets better and better by positive and negative data. So yeah. So it's a company asset in the end. Yeah. Oh. Yeah. Yeah, of course. I mean, mackerel is not just mackerel, and you have different, I'm going to say, schools of mackerel, and also yellowfin tuna with the tuna. So you of course need to get always the captain or the fisherman knowledge before you train the model. Is this the same, or let's say, so we use the word DNA and this one, because it really don't behave like the same. Let's say now the cable in this year or 2 years go north or south. So you of course always need their input before we hand out the model. Yeah. 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 But it will be really interesting. We're opening the model up now, so you saw just 78% accuracy. Now in the next months, it's not only going to show that, it's going to tell you which ocean variable is too high or too low affecting the model, because of course 78, I mean, it's the highest chance, but it varies on the ratio of each variable inside the model. So that's going to be it's going to be insane to see it. Yeah. Anyone else? Yeah, perfect. Don't hesitate to reach out. This is my email here, and you can also find me on LinkedIn. But any idea is a good idea, so please bring it up to me. So that's why we use it, Greenpeace. No idea. Every idea is a good idea. So yeah, perfect. Thank you. Oh, sorry.
Yeah, thank you. Okay, yes. Hello, everyone. It's really pleasure to be here with you today. I am National Academy. I'm working at AFRO. I'm ocean modeler. So today, actually, in this presentation, I'm going to first start to have very short introduction about what we are doing at AFRO, and also what is ocean modeling and what kind of ocean modeling we are working with at AFRO, like ROMS and ocean animals modeling. And then after that, I will discuss about initial and boundary condition that we are using for ocean model, like ROMS and ocean animals, as I said, which is coming from Marine Copernicus service. So then I will show you some results, and then after that I will also discuss about some other projects, which is also, I mean, people also are using of Marine Copernicus service for their own project, for instance, Kaplan distribution, chlorophyll concentration, and etc. So, yeah, but before going on, I would like to introduce you my colleague and my boss at AFRO, and people that we are working. Heron Iglisottir, she's a head of environmental division at AFRO, and Andre Makrander, our oceanographer at AFRO, and Ravi Prakash, he's also ocean modeler at AFRO, and we are also do like international collaboration in this ocean modeler. It's on Pisa Berezina, a physical ocean modeler from NIVA in Norway, and Cecil Erenbjerg, if I'm not mistaken, computational oceanographer from Faroe Island. And also other people that they also use some case for their own project about, I mean, from Copernicus data. Teresa Sofia, marine biologist at AFRO, and Sarah Harzardottir, our phytoplankton specialist at AFRO, and Naya Loran, a biologist at AFRO that is here today, and Theo Karpazoglu, our physical oceanographer at AFRO. Yes. So in general, what we are doing at AFRO, we have three main tasks. First of all, environmental monitoring and assessment, like including temperature, salinity, current, plankton, and fish stocks and agriculture carrying capacity project. But in order to reach some result and to have some advice about, for instance, agriculture carrying capacity But the question is, what is ocean model? I would say just simply and briefly. Ocean model is a representation in the form of some equation, some mathematics and physics equation and computer code which describe physical process of the ocean, like as I said, temperature, salinity, and etc. But among different types of ocean models that has been used by scientific community for diverse range of applications, at HAPRO we are working firstly with ROM's original ocean modeling system, and then relatively new model in general, and also at HAPRO, ocean and model, for which purpose actually to understand about the spread of the salmon lice and distribution of the capelin larva. So, and also many things that I don't want to go to details about all of them actually. But what is ROM's model? Actually, ROMS is a terrain following vertical coordinate and hydrostatic equation model, which is written in Fortran, and it was released in 1999. It's about 2 decades that oceanographer and scientists they are working with ROMS, and it's still under development, and sometimes we see some new capability of the model. But ocean and gas is a hydrostatic and non-hydrostatic simulation model, and it's written in Julia programming language, and it's also possible to run the model in CPU architecture or GPU. But of course, in GPU it's more faster, like very faster than CPU. So here I just wanted to give you a very short introduction about the modeling part. But in general, in order to simulate realistic ocean dynamics and run a model like ROMS, we require several input forcing files, including grid file and bathymetry, as you see here, for 2 kilometer resolution in Iceland, which define the model domain and seafloor topography, and also initial and boundary condition, river discharge, tidal forcing file, atmospheric forcing file, and so on. But here, initial and boundary conditions are coming from Marine Copernicus service. So yeah, as I said, initial and boundary conditions that we are applying to run the ROMS model are from Marine Copernicus service, especially Global Ocean Physics Reanalysis product, which is known as GLORIS data. And the data set here spans from January 1993 until December 2025, including daily and monthly data and variables like sea ice velocity and sea surface height, and and so on. And it's also important to note that horizontal resolution in this data is about approximately 8 kilometers, with 50 vertical sea levels. But the variable that we are using for our model, they are just including seawater potential temperature, seawater salinity, eastward and northward velocity. In order also to validate our model, we are also employing Marine Copernicus service, which is the product name here is multi-observational global ocean sea surface salinity and sea surface density. Especially we are using just sea surface salinity to validate our model output. That in this slide we will see a ROMS model output, which is covered 2004 year 2017. Here you see sea surface temperature from ROMS output and sea surface salinity, which is it shows really in overall good match with satellite data. I mean SMAP and SMOS data, and also very high resolution data. Yes. So we are also validating our ROMS output with observation data from HAPRO or CTD data that you see here. For instance, for CTD section, for instance, here in Latrobe Yard, you see ROMS sea surface salinity against observation sea surface temperature against observation sea surface temperature, which is really quite good match even with observation CTD data. So, but this data it's important to say this data is available at HAFRO website, coro.hafro.is, if you are interested to take a look. Of course, the smaller details. And another one is actually is Ísafjarðardjúp case study, is ocean animals model. And Ísafjarðardjúp actually is the largest fjord in Westfjord in Iceland. But for which purpose? Actually, we are studying risk assessment of salmon lice, which are spreading between agriculture sites. And here in the Ísafjarðardjúp, you see agriculture sites in Ísafjarðardjúp, which is through like squares or rectangular, as you see. And so we are applying ocean animals model to understand about this spreading of salmon lice here. So I would like also to show you, this is just a preliminary result from ocean animals model. It shows sea surface salinity. It is still under development, and it's just some new tuning and modification for the model. Okay, as I said, for the boundary condition of another model, ocean animals, we are also again using Marine Copernicus service. And the product name here is Arctic Ocean Physics Reanalysis from Topaz data for Ísafjarðardjúp agriculture carrying capacity. So I don't want to go to details about the product, maybe, So, but besides the modeling part, at HAFRO, people are also working on other projects, and they are using and employing Copernicus data in their project. For instance, I would like to point out to Kaplan project or Kaplan distribution. In general, actually, Kaplan is a migratory pelagic fish species, which is economically very important fish. And what they do, they use the Copernicus data to predict distribution of the Kaplan in the domain area that they are studying. So what kind of variable they are extracting from Copernicus service? They are including temperature, salinity, dissolved oxygen, and also phytoplankton. And maybe it's also good to just to say the name of the product that has been used at HAFRO. It's Global Ocean Physics Analysis and Forecast and Global Ocean Biogeochemistry Analysis and Forecast. So Teresa, that I have already introduced her to you, she's working in this project. I mean, if you have maybe more detailed questions, you can send her email. So, but another use case of Copernicus data is aerofoil data, which is a part of Copernicus climate data. So, that a colleague of mine told that I have already introduced this to you. Actually, he's just using a monthly average to correlate our data to understand the variability with the Copernicus data. And this is another use case, and another one is observation and product views for chlorophyll concentration, which is from Atlantic Ocean satellite observation that providing biogeochemical products. What they do, what is the purpose? To understand about concentration and distribution of the chlorophyll in the, for instance, here in Westfjord. As you see in this figure, which is for 2020, 4 months. It's a sample point in open ocean here. It shows the distribution of the chlorophyll from 0 to 10 in this figure, you see. And yes, and then regarding this project, of course, there are it's still under working and under development, and future implementation regarding that, along with the data simulation, we can use our extensive data set with Copernicus to do, for instance, regional bias correction of satellite chlorophyll, and use biopigments to detect why errors happen, and separate active versus detrital, especially near shore. And Niall, my colleague, is working on that this year. So maybe if you are interested, he can give you more information about what's going on about chlorophyll concentration. Yes, yeah, thank you so much for this event, and thank you so much for your admission. Yep. Any questions? Yeah. Yeah, yeah, yeah. Actually, one of the main important purpose of the modeling is increasing the resolution of the area that you are working. For instance, Copernicus data is maybe I go back to show you something. Yeah, the data here that we are employing from Flores data to provide initial and boundary conditions for the RAMS model. It's just the resolution here is just 8 kilometers, but we are applying for the model to reach to 2 kilometers resolution. And then after that, for the future, of course, we're gonna increase the resolution for like 100 or 2 meter resolution. Yes. Yeah, in a small area and fjord, yes. Yeah, yeah. Yes. But I cannot, yes. Okay. Yeah, yeah. Yes, actually, this is a good question. It's also possible, of course, to use the Flores data for ocean and Ingalls model, but ocean and Ingalls case is a kind of uh, just this one is just for test case, and then we are just using Arctic Ocean reanalysis because it has a thinner layer near the surface, and for a small fjord it could work better than. But it's just for test case. But eventually, what we're gonna do, we're gonna get output of the ROMS model, 2 kilometer resolution, and apply it as the initial condition for ocean Ingalls because it really needs to have a high resolution data. So it's like, yeah, yeah. It's based on, the ROM is based on Copernicus global. Yeah. I mean, in terms of modeling, I think the Flores data is better because it has more resolution, 8 kilometers. But Arctic 1, it has still 11, I think, still 60 kilometer resolution. It has, of course, less resolution than Flores data. But the point here is it has, as I said, it has a thinner layer near to the surface. It will help more for the for ocean and gas modeling. Yeah. Ocean angles, no, I mean, yes, I am also working on, just currently running ocean angles in CPU. It's really slow, and it's really slow. I mean, it's very important to run it in GPU architecture. It would be much faster. For instance, it's 1 week that I'm running ocean angles in my laptop. It's just after 1 week, it just works for 3 or 4 days, something like this. So it's really you can just run it to understand your model is flexible and it's working very well, and then you can switch it to GPU. It's not difficult. No, I don't have, but it's very slow, very slow. Yeah. 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 From the Copernicus Marine? Yes, I mean, in the very near future, yeah, I mean, actually, the plan is nesting the model. I mean, this is the model that I show you here. Maybe it doesn't work anymore. Okay, it's okay. That I show you the for 2-kilometer resolution model. The plan is in the future we just downscaling the model for a small area, and but the initial condition it's not going. I mean, we are not going to use Copernicus data for downscaling the model. It's gonna come from bronze. So yeah, I mean, yes. That's about your question. We are just validating our model output with observation data, CTT data from APRO, and also some observation data from satellite data from Copernicus service to just compare them and validate the model. Yeah. Yeah. Okay.
And good to see the group. I might have to ask somebody a little bit more about Blue North, but we'll have time for that later. My name is Inga Jónsdóttir. I'm working at the Faculty of Earth Sciences, University of Iceland, and I'm just going to show you very briefly how we've been using Copernicus data in some of the projects. First and foremost, the sea ice. Basically, sea ice data is very time critical, and we use all the data types we get our claws on. Sentinel-3 data, relatively low resolution, will indicate likely ice formation patches. Also gives a bigger overview. See here, both the multispectral and the thermal. Well, actually, you don't see it really well, but you have to take my word for it. Then our absolute favorite, the Sentinel-1 radar data, very reliable. Once you get used to interpreting this data type, then there's no going back. It's just so nice. And if I'm being asked what kind of addition I'd like, then having slightly higher resolution, higher time frequency, or temporal resolution, basically. And then when conditions are good, the Sentinel-2 multispectral is also very good. All of this is combined with all the data sets, of course, as well, AIS, to try to filter out what are ships and what are icebergs. And we work a lot with the Icelandic Coast Guard for ground truthing and further kind of study of the ice. Also, the International Ice Tracking Working Group that has very strict standards. These are not quite as colorful as geological maps, but close. So this is a kind of typical sea ice standard that the International Ice Tracking Working Group has developed. And the basic idea behind that is that people shouldn't have to learn new kind of symbology depending on where they're sailing. Recently, there's also a collaboration with ICES in kind of getting the data into their kind of data set. Now the main parameters is sea ice extent, sea ice concentration, icebergs, drift, and sea surface temperature. And I must admit, I'm mainly using the actual real-time data because that's what is the most useful, quite frankly. But there are really nice viewers and API sources where you can get all kinds of other data to see things in perspective. Basically, you can define an area and get ice statistics, mainly based on passive microwaves, so it's slightly less resolution, but for getting the big picture, that's really useful. We've also been using Jupyter Notebook and Google Earth Engine to define specific regions, to use even the radar data to get some indices for certain regions. So this is one topic. Another topic is monitoring the coast or coastal changes. Now the south coast of Iceland is a really nice place to study that. Lots of changes. We have data sources going back 120 years roughly, but more recently, obviously, we use Sentinel-2 and 1 quite a lot. I know they're not highly that high resolution. Sentinel-2 with 10 megapixels at best, and Sentinel-1 goes slightly higher. But to see changes, both long-term changes, and having the timing really good, so it's possible to link with tides and stuff like that. But you can also, because you get images so often that you can actually see certain changes after a single storm, for example. And so we've been doing that a lot. So this is in collaboration with the Icelandic Road Authority and the Katla Geo Center as well. And one of the things we're watching now, this is from the 7th of February, so the kind of easterly currents, kind of winds, have been blocking some of the river outlets, and this is happening here on the south coast. And behind that, you have a little lagoon that is filling up. It's actually frozen over now, so it's not changing a lot. And but you can maybe see that the water is kind of flowing sideways. It's not that unusual, but it's nice to see on what time scale it's happening and what kind of processes are affecting it. This, however, is a more long-term study with the Road Authority and Katla Center, and looking at coastal changes all along the south coast. Our student, Alexandra Kalaur, she finished her master's presenting kind of more in-depth study into how it links to the wave action. And we're also looking at what other factors affect the coast, glacier outburst floods, and it's very easy to see from various images, obviously, which lagoons are affected by tides, which ones aren't, and obviously all kinds of other things that we can look at. And pollution, that's also in collaboration or kind of mainly steered by the Icelandic Coast Guard. So basically the EMSA CleanSeaNet organization, they have a real-time analysis of potential oil spill patches. And then there's a group here that analyzes, okay, what is it likely to be on oil spillage from a ship or from other activities, or is it something else? New ice formation, algae, even currents can also look like an oil spillage. So then it's really good to have access to previous radar images showing how the area was maybe 12 hours ago, or look at some of the Sentinel-2 images to see, okay, is there something else likely to be the cause. I should also mention the Environmental Agency of Iceland, who's also in this kind of working group. And this also plugs in AIS data to see, okay, was there a ship sailing anywhere nearby when this happened? And this kind of collaboration then decides, or it's on the basis of this analysis that the Coast Guard needs to kind of decide whether they have to go out and study things in more detail and take samples and stuff like that. So really important data source for that. Now, other potential uses and possibilities. Now, one of the things, it's not politically correct to say that I'm waiting for this, but this type of data will help us once we get a submarine eruption. Then we can both use the radar and the kind of more kind of multispectral images to verify that something is happening at the bottom. I'm really excited about the news about the nighttime imagery of Sentinel-2. We apply for this for the Landsat data every year, so that's why we are getting a kind of nighttime coverage of Iceland. It needs to be justified, but again, not politically correct, but luckily we have enough reasons to support that with floods and eruptions and things. So I'm really looking forward to it if that goes ahead. Now, other uses, ocean color and currents. We've spotted iceberg calvings, schools of mackerel, mainly mackerel, but it was interesting to see the presentation from greenfish here earlier, because there are such potential of kind of getting more from the data, and also for security reasons, you could also try to find ships that are not within the AIS system. Now, we have lots of students that are working on these data sets a lot. If I'd had more time for the preparation, I would have probably given you a list of what has been done and what is currently, from my knowledge, being done. But I think I'll end with a kind of picture that is hardly ever. So it's a sea surface temperature image from Sentinel-3 and unusually cloud-free. Thank you. Any questions? Okay, thank you.
they were able to. They also generate some energy that other animals they eat, but actually they are not very good food. And this is the point that I wanted to make, that they don't have a lot of nutrients for the other sort of organisms. But chlorophyll, the satellite that we're going to show today, do not distinguish between these and the other. So that's one of the key points. So far, like, we just went very quickly to what phytoplankton 101 will be, or plankton 101. So it's quite, what I want you to take, the take-home message right now is like, it's everywhere. Basically, this sort of phytoplankton bloom here means that once you have a lot of these organisms that they got close to the surface, then they increase a concentration locally, and that is a bloom. And that means that it's likely that there will be could be a lot of other organisms around, because there's going to be like a food chain ongoing. And there are more things for the recipe. So we already said that they need light for the energy of doing all the process, but they also need to be close to the light. And this is going to be important for the exercise that we are going to do just like next part. So most of the time, when they're like, so the ocean has many layers, and these layers, they change over time. So during the winter, these layers, they can get really thick, and during the summer, they get really shallow. And within this layer, you could think that all these nutrients and those larvae that are just waiting for the sunlight to come, they are just living there. But when they are like really far from the sun and there's no sunlight, so in the winter, they will be like somewhere around here, there will be no phytoplankton because they're just not close, one, and there's not a lot of energy, at least our latitude. But once you get closer to the summer, or starting in the spring, then these organisms get closer to the surface, and then they actually get close to the light, and then these can start, the process can start. So usually we have what is called the spring bloom. That's the phytoplankton bloom. It starts sort of in the spring. And so if I love cooking, so if I could put everything in a recipe, this is what you would need for a phytoplankton bloom recipe. So the ingredients that you need sunlight. We need a lot of sunlight. And something that I forgot to say is that you need nutrients, and you need somehow those nutrients to make it to that layer. And that is one part that is going to be important for many other, for the exercise that I'm going to show later. You need water to be stable, so that mixed layer, so that layer that I said has to be closer to the surface, has to be stable. So it has to keep those organisms close to the sunlight quite for a long time. And you also need the right temperature. So when temperature changes, these things can change. And then you need basically the larvae that was out there ready to be blooming. And what you do is you just add that plenty of light. You steer in the nutrients. So to steer in the nutrients, that means that you bring those nutrients to that surface. They get closer. And let the water settle, because it has to wait a little bit. If you have a lot of storms and that layer gets thicker again and thinner and thicker and thinner, it's not going to do it. So it's like a sourdough. You just let it just wait. Like wait a few days. And with sunlight and all these things, this might multiply rapidly. And once it multiplies rapidly, you just serve it as a bloom. And that's, voila, you have your ocean has a bloom. And that's what we have. And how does this look actually around Iceland? So around Iceland, I show you this one. It's one of my favorite pictures because it shows very clearly the blue and the green in the south. But we, almost like the north and the south in many countries has been divided. So Iceland is not the exception in terms of oceanography. So the phytoplankton bloom in the north is completely different than the one in the south. And it's very counterintuitive, which I find fascinating. So this is a time lapse. This is from here it is. The paper is from 2012, and it's one of those first papers that we looked at sort of that behavior. But look at the year, because the years that we are going to look, they have some changes. And I think that will be important to show this type of changes. This was in collaboration with Hafro as well, that study, I believe. And if you move from March, April, May, then boom, red is like like a bloom. So the bloom starts in the north. And to me, the counterintuitive part is that actually the north has less light. Like if anyone has lived in Ísafjörður and you know that the day that they actually see the sun is later than what we have it here, then you understand that. And in my head, I always thought like phytoplankton should know that. Like they just get the light later. Like why are they blooming early? And then you move June, July, and then eventually like, okay, yeah, some phytoplankton bloom starts here, and starts here, everywhere. But the main one just started in the north. And that's the sort of the exercise that we could actually do today. I'm going to show how do we do it with Copernicus. And then once you are in October, you know that Ísafjörður has no more light. That's why you don't have any more data in chlorophyll for that. So again, like now in modern Copernicus, how will this look? I'm just going to show it now, but we are going to actually poke the computer today, and I'm going to show you how to poke that computer. So here is January, February, March, April. So here in March starts already earlier. So one of the things that is happening in Iceland is that the phytoplankton bloom is actually starting even earlier. Like that one was in May, now they are actually starting earlier. And what are those changes? Those changes, you can see them using Marine Copernicus. But you can track these variables from 1993 until 2025 in some reanalysis, but you can also do from 2022 to 2026. And actually we can see, today we will see, you can see the prediction of that in 10 days. So basically what Greenfish uses is this. This is one of the main tools for that. You can get that prediction. So we have it here, like in the north. It still follows a little bit like what I was telling you, that it starts in the north and then goes relatively. So the south for this particular year, or this, it was not quite there. So again, like just to go to that review of the ingredients and why is this one is going to be interesting compared to the one that any other place in the world, is that I told you that we need sunlight, but somehow the north has less sunlight at some point. So here I'm trying to, sorry, I think I put it opposite. Sorry, I put it opposite, but this should have been the north. So it actually, the bloom starts earlier, will have started earlier, and then in the south it will start later. But the weird, we found that there's the difference, and this is something we published last year, is that actually the north, that mixed layer, that layer, it's always thin. Like no matter if it's winter or summer, it's just about the same size. So the larvae is always exposed to the surface closer compared to the south. In the south, that layer goes all the way to, what is that, like 600 meters? And in the north remains about in 100 meters to 50 meters. So the phytoplankton is there like ready just to bloom. Like it's just, like I'm just waiting for summer to come here, but it hasn't come. No, it's all right, I'm so close to the surface. But in the south part, it's just too far away. So it really has to wait. That's what that one delay. And before, I was not really sure if we were ready to just jump in this one, or I'll give you a very quick other example that you might have read of why is important phytoplankton. So I decided I'm going to go through that and I'll kill it. So 2025, there was something very, it was on the news everywhere. There was like what's called like a missing bloom in Panama. So in Panama, there's a bloom that often used to happen in this area, a phytoplankton bloom. And suddenly in 2025, they just didn't have it. And it's like, what just happened? You know, fishing industry was just ready. Like, we are just gonna fish all this. And like, where is the bloom? And if you don't have a bloom, you don't have a start of the chain. And if you don't have a start of the chain, Panama has no fishing to do for that period, which is very bad, very bad. So for that, I'm not gonna bother you too much with this, but we actually prepared one product that we are gonna show in the workshop at in April, I guess, in the spring, like just like the bloom. That product is gonna show how we can actually show that how can actually prove that this bloom was missing. And so this paper that was really nice showed that actually the waters were really warm. And if you remember the recipe, the bloom should have also the right temperature. So if it doesn't have the right temperature, it might actually not bloom. And what happened here, like we're going to show this in the showcase for Iceland, we're going to show it. But I did this for class that I was teaching, and I showed them that you take an area in Marine Copernicus, that's the one that we are going to show later today, just after this, and you can look at the variables. So which variables we need? So one of them could be just the phytoplankton, the concentration. So that concentration of phytoplankton here is time, and here is the concentration average in all these areas. So all these areas have been averaged, and we can see like 2020, what is that? 2024, there's a peak, that means there's a bloom, and 2025, no bloom. Like boom, it's gone. And then another proxy that we can actually look at is the temperature. Because when the bloom comes, sometimes nutrients come from the bottom, and usually they are related to some cold water. So the temperature at the surface, here it was cold, here it was cold, and here it did not change. So that means that it just never got nutrients. So these did not get nutrients at all during that period. And it's like a 1 year that is gone. Could this happen in Iceland at some point? Maybe. Maybe in Iceland we are seeing changes in the north and the south. The north is blooming earlier, the south is blooming slightly less. So those are sort of the proxies and things that we can do. And just before, again, like I move to that one of the things that I wanted to mention is that we can actually give back to Copernicus, or these services, they require data back. And it would be fantastic, for example, if we can provide more data from every data that is collected, that it can be given to them, so that the product that we use for this analysis that people might use for the models or their publications, they could actually include it and improve their models as well. So there's this organization, and I know this organization because they started in New Zealand, and it's like Fishing Vessels Ocean Observation Network. So basically, you can take all the fishing vessels as ocean observation platforms. So in the ocean, we have like already we talked about like all these platforms in the open ocean, but there's a huge gap in between the coast and what happens in the open ocean. So if you look at how many fishing tracks have been ongoing last year, so this is all the heat map of that. And this is only for the trolling ones, which means that you can get a profile all the way to the bottom, and you can actually get a profile of temperature or any other variable if it's possible. So it will cover a huge area, and this is a little bit how it works. So you can see here in this map, New Zealand basically adopted all the vessels, most of them, Australia as well. And now we have, this project has 3 in Iceland that are ongoing, 3 in the Faroes as well. So when the net goes down, or anything that goes down, has a sensor and it collects the data. Once the net comes back, that unit that is there, it retrieves the data without anyone touching it. It's like just there, and it talks to the satellite, or if there's cell phone signal anywhere, and it sends you that profile, and you can get a profile of temperature within 2 hours. And actually, Copernicus starts adopting this one, because if you get that profile, it's great for your forecast, because you know exactly what the temperature was at that point, and you can modify your model or nuke a little bit so you can actually get it. So it's a little bit what we can give back. And I guess, like, thank you for this part, but we are going to move for the demonstration. So if anyone has any questions about this, please feel free to do it, and we are going to show something else here. Yep. Yeah. Yep. Yeah. Yeah. So that puzzle is more complicated than that. So there's something that we call alpha and beta oceans. So alpha ocean is something that is driven by temperature. So, and beta ocean is something that the profile of density, so the density in the ocean is driven by salinity. And with temperature is fantastic because you have a flux, that is the heat flux. So it's like your cup of coffee. It's hot, you blow on it, and you do something that is like heat flux. So you extract heat from it, so that parcel of water just goes down, and you generate deep convection. But with salt, there's no mechanism to erode the salt part. And it turns out that the maximum of salt is just exactly at the mixed layer, maximum mixed layer depth that you can get. And salt is the one that controls that mixed layer. So it's not, so temperature vanishes because it's colder. I agree with you, it's colder. And that's the other part of the puzzle. It's colder, but then it doesn't, there's no mechanism to remove the salt. Like you will need to freshen it. And we have done that in the class. I put the students to calculate how much fresh water you need to add so that you erode that layer. And there's no mechanism to do it, which is the main controlling part in the north is the salt. It's a beta ocean. And the south, because it's Atlantic, alpha ocean. Oh yeah, we're gonna see that. Yeah. Mm. We're gonna see it now. But that one is it's true. It is a lot more variable. It is. The peak is very sharp and clear in the south, but in the north is more like an. Any other questions? Burning questions now? Well, I was always told that you should never program in real time, and I guess I should have not done this. But I think it's good that you see that actually a human being can do this type of process. So I'm just gonna show you how we do this type of calculations. I'm gonna change. Sorry, I'm gonna sit because otherwise I'll. So if you get convinced that My Ocean Pro and Copernicus is a good tool, eventually you might actually explore this website. And if you explore this website, the first thing you will come up with this one is explore the ocean. So this is what we are gonna do. So like we go to this My Ocean Pro, and I just go and open this one that is Explore My Ocean. And by default, the platform gives you some variables. You need some variables that they decide that is what you want to see. For this case, I don't want to see these variables. I don't want to see the sea water velocity, and I do not want to see the potential temperature. So potential temperature is just, by the way, another way to say temperature, but in an adiabatical way. Just a fancy way, it's temperature. At the surface, it doesn't matter. It matters at the bottom. And certainly we have the one that I need, but I'm gonna put it like no layers at all. And if you have ever used any GIS system before, you know that they work on layers. If you are as old as me and you ever used CorelDRAW, you learned that you put layers on top of one another, and it's kind of a way that we can visualize data. So in this case, we can add a layer, and as you saw in the nice presentation from Marco, you could take a look at all the products, 303 products as in for today. But today we are going to look at only the global analysis and forecast, because I want to show you that you can actually forecast some of these data. And we want to move in the green ocean. So we are not in the blue ocean, even though I'm a physical oceanographer, but green ocean is such a good proxy for the blue parts. So I'm going to add to the map. And the first thing that I want, so there could be many things. You can look at CO2, you can look at nutrients, you can look at the optics. And the reason for optics is that is actually the measurement that you get. You measure optics, and then you say like, oh, this wavelength belongs to this chlorophyll, this other optic part belongs to this. So the chlorophyll is an interpretation. It's actually not a measurement. The measurement is to go out and collect the water and get those animals that I showed you at the beginning. And you will need to measure millions of those to do that, but because they sort of shine at the same wavelength, so that's what we can get. And then what we're gonna do is we're gonna look at daily data, because then we can see the variability that was mentioned before. So the variability of phytoplankton daily. And what I want, if you are a chemical oceanographer, you might want to have the millimoles, but because most of the people that I work with, we like milligrams per cubic meter. So I'll add it to the map. And now it's added to the map, and we are like happy. So what we have now is added this variable, and it has a default sort of bar. So I'm just gonna hide the bar, and because I want to be really like centered in the North Pole, I'm gonna move projections. So I want to see a projection where I can see Iceland a little bit more in an isolate. You can zoom in, and things that are important to mention is that Copernicus is the resolution that Masume mentioned. Is great to mention it, but here you can even see it. What is the resolution? So you have actually, if you look at the size of the squares or rectangles here, you can actually see that Copernicus does not see qualflow. So if you are gonna tell me that with this data, you can see what is the fish that is in qualflow, I'm just not gonna believe it. I just can't do it. It does very well for the open ocean. The open ocean is not bad, but coastal part, and that's why that reaching that gap with sensors or other type of observations is great. You cannot really do it, so you need like high resolution numerical models like what they will develop. But nevertheless, like let's just keep here. This is our Iceland part, and just zoom out a little bit so that we can get the part of the north and the south. And right now, as in today, there's not really a blue. And we can push it all the way to the forecast that it has. That is, I think, 27, and it will change a little bit, but sadly, there will be no bloom in February. So we need another year to do that. So let's just go February 2024. And we start moving on February in time. So we start in March. And the color, as it increases, it basically shows you what is the concentration. So now I see kind of like the starts to bloom. And again, what I told you that starts in the north is happening. You can clearly see that it's starting in the north. But let's just quantify it. We could actually do quantify. So let's just put 2 points. I'm going to put 1 point in the north and 1 point in the south. So let's just put 1 point here, drop. You can imagine you go out on a boat and you drop your point and you are going to measure something here. By default, it's going to give me some plots that I don't want. So I'm going to remove them. We go to this 3 dots, remove from the graph, 3 dots, remove from the graph. And then what you get at this point is a time series of the chlorophyll for the time that the model has data. So I told you this sort of version of the set is from 2022 until 2026, 10 days plus today. And we could do exactly the same for the south. So we take another point taken, and we go south. And in the south, it's going to do the same. It wants to give me extra information that I don't want. And I just remove it from the graph. But now we have the sort of the 2 plots. And that blue line that you see there is the day that it corresponds to that timeline. And I think right now you cannot really see that one bloom starts earlier or later. So what we need to do is to make an adjustment in the axis. So by adjusting the axis, I just want to look at 2024, for example. So I just go 0, 1, 0, 1, and do 2024. And I could go 0, 1, 0, 2, it doesn't really matter, 2025. And apply, and it has moved. So now we have just 1 year, and we need to do the same on the other one so that we actually can look at the same. So it was 0, 1, 0, 1, right? 2024. And then the other one is fine, 0, 1, 0, 2, 2025. And we apply. We can actually ask it to make it a little bigger. I want to maximize things, and we maximize these things here. and we try to compare them. Oh, yeah, okay, now we can actually compare them. So we merged them in the same plot, not exactly what I wanted, but nevertheless it happened. So what I was mentioning about that north and south and how things are changing around Iceland, that paper was in 2012, and for some time it was exactly like that mechanism. We had like the bloom will have started, or like maximum will have started in the north compared to the south, but now suddenly there's some things that have been changing in the past years, and this is a good tool to show that those things are happening. So as we heard before, the north has a lot of variability compared to what the south has. The south has a lot, the peak is a lot clearer, but now there has been some shift on that, and that becomes interesting problem for like scientists, but it's also what I call it like a warning sign, because there's something that has been changed. Whether this one makes new pathways for species, alien species or something, that I don't know. And we still don't know which type of plankton is here. So which one is the one that is increasing now or decreasing on the other side? We don't know that. But that is sort of like what you can do and play with Copernicus. As I said, it's relatively, I use it so much that that's why I'm easy with it, and I can make plots very fast or make this type of data sets very fast. But you can also export everything as a TXT file or some CSV file that you could read in Excel. If you want to make this plot in Excel, if you want to be fancy and do it on Python, MATLAB, or R, or anything else, you can export it as a net CDF, or like many other of my students do, is like I ask them, you only need to make a figure, so you can export it as a figure, and they just can paste this one on the on their homework sets. And with that, you can not only do this around Iceland, you can actually explore the entire globe. If you ever wanted to explore the phytoplankton bloom in California or in Peru, or that one in Argentina or something, you can just go everywhere and look at any of the variables that exist. So with that said, any questions? I'm very happy to answer any questions about this part. Yeah, that you could choose, and actually to answer that question, I think the best is like if you want to check another point, you can very easily just drag the point further, and you can drag the point further. And in my opinion, using just one point is a little hard to make conclusions of that. So why don't we do what exactly we did in Panama? So you can actually look at an area. You can go and draw. Ooh, sorry, my mouse is not cooperating. You can look at some area that is what I would think north, and look at the chlorophyll there. And you could also look at another area in the south. But we have done this one for that. I could send you the link of the paper, but for most of the years before 2022, the north in the same region started consistently earlier. And then after 2022, there has been some change. We don't really understand. We don't know why, but right now it's just for the observation of it. But we could do like the south, for example. You don't. Yeah, one more thing that I forgot to mention is that the north of Iceland has almost no eddies. There are no these things that spin around. They're not as active in the north. Oh, no. in the north of Iceland as they are in the south. So here you have the two plots. Yeah, I think it's hard to look at it, but right now, as if I would have been in years before, like even I think this year might actually show that a little bit. Still, the north has more chlorophyll before that sharp peak. And if you zoom in this one, it's about 6 weeks. And I think some very nice study for a student will be to count how is that delay been changing over time on the peaks in the two different regions. But now we need students to work on this. They are like that. There seem to be two. I don't know. Yeah, it's in the south is really it just happens it's a very sharp peak. This is what I forget his name, but he was mentioning that the north has a lot more variability, and you can actually see the north. There's like the variability is a lot more, and what we did on that paper is to quantify basically the integral over that curve, like the total concentration, and compare those two. And it used to be actually a little bit higher in the north and in the south, but in the when like a year ago that was sent or published, and it was no more difference in that year. Yeah. Yep. Yeah, let me just get back to my recipe, I guess. Yeah. So in the south, what happens is that this layer here, it's very thin. Like it's very like 100 meters, and it changes from 100 meters to 50 meters. Whereas in the south, it changes from 600 meters to 50 meters. And it takes a bit of time, but I think probably the phytoplankton, the larvae, is so ready to bloom that once it reaches the necessary factors, then it just blooms. And the nutrients, they come from slightly below that sort of layer. And they could still be probably feeding on some nutrients, but if they don't get the sunlight, or they don't have access to the sunlight, they will not bloom. Because that's the most important is that energy they get. Because that's almost for like in the north for almost half a year they don't really bloom. So I guess they are like little bears that are just like going and sleep for a while, or the larvae just take some time for that to bloom. But yeah, once they bloom, apparently in the south, yes, I agree with you. Like that peak just goes really fast. Whereas the north, I think they have more time to do that because they probably are closer to the surface. They don't need to. But I think I find this fascinating for Iceland because it's very unique. But now it's changing, so that uniqueness seems to be dying out. Anyway, thank you very much. Oh yeah.
I don't know, with the exercise, I think we can make one group and do it together. So, thank you very much, Angel, for your final, amazing presentation. For those who are online, we prepare some
I would say, interactive exercise, a dashboard where we would like to get information like your feedback, how you are using Copernicus data in your work, what are the barriers, what are the challenges, and also where you would like to see this Icelandic, this national Copernicus activity see in this year 2026, like what kind of activities, or what you'd like to see directly from the Copernicus. So for those who are online, they can use the QR code and or the URL link. We will work here with paper and pen. And also, before, I would like to briefly say a little bit about the survey what we ran in December and early in January. I think most of you answer that survey. We got like 68 response. I think it's quite a lot. It's really nice. And from that, we found that 74% are non-users. People mentioned that they never use Copernicus data. And from the small amount of people who already met with Copernicus data or a little bit worked, they usually said that they have some tactical or technical problems. And yeah, and also most of the users were from the research or public agency. So also from the results, we see that the main domain was marine ecosystem monitoring, coastal and fisheries related analysis from the research. Then the top rated variables were currents, temperature, or tides, and also users said that they are mostly interested in GIS-based integration. And from the training topic, like the people were mostly interested in introduction of Copernicus Marine data and its main product families, or how to access and download the data. From the challenges, most, as I mentioned, I see that this wasn't on my presentation. Something happened that all the, yeah, seems like all the spaces between words are missing. So like from the reported challenges were reported technical complexity and practical workflows that we need to focus a little bit. Then of course was a lot of mentioned resolution, and that, as I said, 47% users didn't use, so that it's a limited operation familiarity beyond the users. And also what would enable stronger use, we found that Iceland relevant examples, to add more Iceland relevant examples, might be boosting hands-on beginner workshop and clear applet guidance. Yes, you can see also here a lot of users mentioned spatial temporal resolution is not sufficient. Okay, so let's start with the short exercise. With Marco, we prepare